Today I will present our work on a multiphysics digital twin approach for understanding and diagnosing cardiac disorders. This project is a collaboration with Dr. Peshalatika Maj, Dr. Bahram Kakavand, and my supervisor, Dr. Amirta Taibi. Together, we aim to link blood flow, cardiac wall motion, and chest vibrations to better understand how heart dysfunctions manifest on the body's surface. Cardiovascular diseases are the leading cause of death worldwide, with nearly 18 million deaths annually, and are projected to increase further. Early detection is critical to reduce preventable death. There are monitoring methods ranging from invasive to non-invasive ones, such as ECG and seismocardiography, or SCG. SCG in particular is a low-cost and accessible technique that captures the chest vibrations related to the cardiac function. By using computational methods like FEM, FSI, and creating digital twins, we can simulate patient-specific anatomy and predict how these vibrations form. We use 40 CT scan images from each subject and manually segmented the thoracic organs, including lungs, rib cage, muscles, and fat, using 3D slicer. The geometry were smoothed and prepared for import into ANSYS workbench. To capture cardiac wall motion, we extracted the cardiac wall motion, cardiac wall displacement using 3D Lucas-Kennedy optical flow algorithm. These displacements were then applied as boundary conditions in FEM simulations that allowed us to study chest vibrations without explicitly modeling the heart itself. In these simulations, we use cardiac wall displacement to model the chest surface motion. Here it shows how SCG signals for 3 subjects are modeled. Here we also visualize the displacement contours across the chest for a full cardiac cycle that highlights how local heart motion propagates outward to measure vibrations on the chest surface. Our previous work demonstrated patient-specific SCG simulations for 1 subject. In a new submission, we expanded the framework to 3 different subjects and compared their simulated dorsoventral SCG signals. We also performed sensitivity analysis. We varied subcutaneous fat thickness, chest muscle stiffness, and myocardial wall motion to mimic physiological changes such as obesity, aging, and exercise. These variations allowed us to study how anatomy and physiology affect SCG morphology and spectral content. In our optical flow FEM framework, we successfully reproduced SCG waveforms that were consistent with clinical recordings. Building on this, our current goal is to explicitly model heart itself. We are developing a patient-specific fluid structure electrophysiology interaction, or FSEI, heart model. With this approach, we aim to simulate realistic cardiac motion and, as shown in this slide, generate SCG signals directly from FSEI heart model. This project is ongoing, and we expect it to provide a more comprehensive and physiologically accurate framework for modeling cardiovascular dynamics and their surface SCG outputs. In summary, we developed a patient-specific digital twin framework that combines medical imaging, FEM, and SCG signal analysis. Our findings show that anatomy and tissue properties play a key role in shaping SCG morphology, and the simulated SCG signals closely match clinical recordings. This confirms the physiological accuracy of our approach. This framework lays the foundation for non-invasive and personalized diagnostics using SCG. Looking forward, the integration of FSEI will allow us to simulate realistic heart motion and disease conditions. Thank you very much for